right, so we are going to be discussing, busted. I already showed you my joke. What do you call it? One molar, what do you call it? Tooth in a glass of water or 1 molar solution? But nonetheless, you don't know what that means yet, so it's not really all that funny. So I'll show it to you again in a minute. All right, so we're going to talk about molarity. We're going to be using it like crazy in the lab starting next week. So we need to talk about it now so that when we're doing lab next week and you're going, what's this capital M? You'll know what it is. And then when we get to solutions, we're going to do it in such gross detail you'll probably want to throw up. So we want to get the baseline now, and then we're going to elaborate on it much, much more later. So as I mentioned on Monday when we were classifying matter, a solution is just another word for a homogeneous mixture, right, which means that it's evenly distributed throughout. And we prepare a solution by dissolving a solute in a solvent. Okay, so right now I've got water. If I take a scoop of Gatorade mix and dump it in there and stir it up, right, the solute would be the mix, the solvent would be the water. And we have a special type of solution. When water is the solvent, we call that an aqueous solution. The vast majority of our solutions that we will be using in lab are aqueous solution, which is why we have the subscript AQ, right? AQ means dissolved in water, right? So the solutions that we'll be dealing with, the vast majority of them, will have the subscript AQ because they're prepared by dissolving a solute in a solvent, and that solvent being water is what makes it aqueous. And molarity, and I underline this to designate it as being uppercase, okay? I know some people write all their M's kind of rounded on the top, even if they're uppercase, all right? You need to really be careful about how you represent that M, because there is another M. It's called molality, and it's a little m, okay? That's not the same thing as molarity. So that's why I underline it so that you can tell for sure with 100% certainty this is molarity, capital M, right? Not molality, little m. So make those points very distinct because you need to see this is a capital M, not a little m. Okay, when we get to molality, I even write that one in cursive just to make it special. So the concentration we're talking about here is the ratio of solute to solvent. Okay, that's what we're talking about by concentration. So the formula for molarity is moles per liter. Okay, the solute must be converted to moles. So if I give it to you in grams, you must calculate the molar mass and convert it to moles. And the volume must be in liters. Now think back to lab yesterday when you did your first experiment. Did we deal with a liter ever? What volume are we dealing with? We were dealing with milliliters, right? Probability of you making 1 liter of solution in this class is probably pretty slim. You're probably going to be doing all your experiments with milliliters. So if you're doing an experiment in milliliters, make sure that volume gets converted to liters before you do any sort of calculations, because otherwise your answers will be grossly off. Okay? And again, I underline the molarity if you want to like really just emphasize the fact that it is pointy mountain peaks, right, to make it capital M. To distinguish it from lowercase m, molality is also a unit of concentration, but it's different. Okay, so we'll talk about it in a few weeks. Questions on molarity, what it is. So this is something I do when I'm preparing your solutions. I figure out, okay, I want it to be a certain concentration. So I figure out how much solvent, how much solute do I need, and then I measure it out, add it to my volumetric flask, which is a very accurate way for measuring volume, right? I measure it to the neck. It's got a mark here on the neck. And that is a very accurate way for measuring volume in large quantity. And then to get molarity, it's just moles divided by liters. Right, so this is something I do when I'm prepping your solutions. I actually make really concentrated solutions and then dilute them, so I don't have to make the same solutions 100 times. I can make a really, really concentrated one, and then I just have to dilute it. So these are the 2 most common mistakes I see in molarity calculations, and I take a point to point them out because you're very likely to make these mistakes too if you're not thinking. Forgetting to convert grams to moles or converting grams to moles incorrectly is the #1 mistake. That's the #1 mistake for sure. So either you convert it to the wrong thing, right? If we convert grams to atoms, that's not going to help us. That's not going to be the right units. It'll be atoms per liter. So make sure you convert grams to moles using the correct conversion factor, the proper molar mass. That's the most common mistake. Second most common is volume. If volume is in milliliters, which it is in lab, all your experiments are going to be done on the milliliter scale. If you take those milliliter measurements and then start doing calculations with them and you forget to convert milliliters to liters, your answers are going to be off. Okay? So make sure you watch your units. Okay? Solute must be converted to moles, and solvent must be in liters. Now, it's easy to convert milliliters to liters, right? You don't need to write a conversion factor. I mean, you can, but it would be milliliters times 1,000 milliliters per 1 liter, right? So you're dividing by 1,000. So if you just remember to move the decimal 3 to the left, that's easy to do, right? That's not a difficult conversion. So let's go through this one together. Calculate the molarity of a solution prepared by dissolving 5 grams of this sugar in sufficient water to form exactly 100 milliliters of solution. So we've got to look at our problem, ask ourselves, are there any conversions I need to make? If so, what are they? And then go through the arithmetic. So is this just 5 divided by 100? I'm done? Is that the correct way to go about doing this? No, right? Because what would the units be? If I did 5 grams divided by 100 milliliters, the units would be grams per milliliter. That's a density. We could use density units for grams per milliliter. But that's not actually the density. That would be something else. It would have the units of density, but it wouldn't actually be its density. So obviously I can't just take 5 divided by 100. That's not going to work. So what do I need to do? Got to convert grams to moles, which requires what? Do I use Avogadro's number or do I use molar mass? Molar mass, which means you need a periodic table. So if you don't already have one handy, pull one out. And I've got some little mini ones up here if you need one. And then can I use milliliters or no? No, got to convert it to liters. Okay, those are 2 conversions we must make before we can do this computation. So I convert grams to moles. Where did this 180 come from? By the way, don't round your molar masses. I rounded it because I was running out of space. I wanted to make this conversion factor smaller. So I just rounded, but normally you carry out those decimal places. Where did this come from? How did I get that? How did I get that 180? 6 times the mass of carbon, right, plus 12 times the mass of hydrogen, plus 6 times the mass of oxygen, right? That's how we got that molar mass. Remember, molar mass of a compound is just adding up all the molar masses of the individual elements. Now look at my sig figs here. By the way, we don't treat this as sig figs, okay? Molar masses we're treating as constants, so they're not going to factor into our sig figs. So I take 5, I divide by 180. This is what I kept. Notice I kept an extra digit because 5.00 has 3 sig figs. I kept 4 sig figs here. Why do you keep extra sig figs until the very end and round at the end? There's a really good reason for doing it. Extra digits at the beginning and then round at the very end. If you round at step 1, and then you take that answer and you round again at step 2, and then you round again at step 3, and then you round again at step 4, right? Your answer is going to end up being too high or too low. We call that rounding error. So carry out extra decimal places and then round your answer at the very end. Okay? Always round at the very end. Because again, this will come into the picture, especially when we're doing things like stoichiometry or colligative properties, when we're doing our thermochemistry calculations, right? Where there are multiple steps. If you round at step 1 and then step 2 and then step 3 and then step 4, you're going to end up with too much rounding. So carry out at least an extra digit until the very end, and then round at the end. Okay, 100 milliliters. How do I convert that to liters? 3 to the left, right? If you want to show a conversion factor just for your own, peace of mind, you can, right? There are 1,000 milliliters per liter. Now, here's the thing. Watch your sig figs, okay? When I move the decimal, does that change the accuracy of this number? It doesn't, okay? A lot of students, I see this a lot. They'll take this 100.0 and then they'll just write 0.1 as their answer, right? And then they'll be like, oh, that's got 1 sig fig, so I use 1 sig fig in my final answer. That's not true, right? All you did was move the decimal. You did not do anything to the accuracy of actually making that measurement. Does that make sense? So if you convert milliliters to liters, if you've got 4 sig figs, you need to keep 4 sig figs. Make sense? Make sense? Now when you divide this by this, that's all you have to do. Molarity is moles per liter. And then we're going to do our rounding at the very end. 3 significant figures. Make sense? Moles per liter. This is a really important concept for the lab. We'll be using it tremendously this semester. Questions on this one? Ready to try one for yourself? All right. What is the concentration of the solution that forms when 2.5 grams potassium chloride is dissolved in 500 milliliters of water? I'll give you a second to jot it down, and then I'm going to pause the camera so that we don't have dead air on the video. So I'll give you a second to jot it down, and then I'll pause the camera while you work. If you need a periodic table, there's one in the back of your lab manual. There's one on the front inside cover of your book. I gave you one, and if you've lost all of those, I've got little mini ones up here if you need a little mini one. All right, I'm gonna pause the video for a second. All right, let's go over this one. First thing we have to do is we have to convert grams to moles, right? So what do we need to do that? Do we use Avogadro's number? No, we use molar mass, which comes from the periodic table, right? So mass of potassium plus mass of chlorine, and we convert to moles. Notice I carried out lots of extra decimal places here. I just wrote what my calculator gave me, right? That's what my calculator gave me, and that's fine. You want to leave it like that and then round at the very end? No problem by me. But you need to carry out at least 1 extra decimal place. Then you should. All right. Now we've got number of moles. How did I get this 0.5000 liters? 500 milliliters, right? And again, this number has 4 sig figs, so it's going to keep 4 sig figs, right? Moving the decimal doesn't affect the accuracy that you used in using the graduated cylinder to make this measurement, right? All you're doing is moving the decimal. That doesn't affect the accuracy of this measurement. That's why you've got 4 sig figs remaining down here. I can't tell you the number of times I've seen students put that and then go, well, that's got 1 sig fig, so my answer is 0.07. That's not correct. I've also seen students do something like this. They'd round it to 0.1. They'd say, that's 1 sig fig. That's even worse, right? 2 sig figs, this 0 is not significant. Not significant. So 0.067. And then for your units, you can write a capital M, which is what I do. The other way that is acceptable to write the units is you just write it out, MOL over L. Okay? That's perfectly acceptable as well. So you can do it either way. You want to write capital M, just make sure to emphasize that it is uppercase, not lowercase. Or you can just write MOL/L. Either one works. Questions on this one? Ready to try another one? Okay, this time I'm asking for something different. What volume of 2.5 molar HCl solution contains 0.0500 moles of HCl? So what variable am I asking for here? Think about it and solve the problem. I'll just leave the camera running this time because this one shouldn't take you very long. So do we need to deal with molar masses this time? No. Now the one thing I will caution you about when I'm asking you about volume is, what is the default unit going to be? Molarity is moles per liter, right? So if you're calculating a volume, by default, the unit is going to be liters, right? Now, if your volume comes out to be 0.003 liters, that's not a very practical unit, right? Because if I handed you a 1 liter beaker and said, put 0.003 liters in here, you'd be like, what? I would too, right? So if you get a liter volume that doesn't make a lot of sense, convert it to a unit that does make sense, right? 0.003 liters, you're never going to get that with any accuracy. I'm not either, right? So convert it to a unit like milliliters that you could accurately measure. So you can do it a couple different ways. I always rearrange the formula and then plug it in. That works. You could plug 2.50 in here, plug 0.0500 in here, and then solve for the denominator just like you did in Algebra 1. That works too. Whichever way makes you happy. You're going to end up doing the exact same things. Now, watch something here. When you do this divided by this, that's what your calculator says, right? Your calculator's not smart enough to know sig figs. Your calculator knows nothing about sig figs. Your calculator's just giving you the number, right? So you need to make sure that your final answer includes the appropriate number of significant figures. And also, like I just said, 0.02 liters, that's not a practical unit, right? A 1 liter flask, you fill it 0.02, get real. I can't do that. You can't do that. Nobody's going to be able to do that. So if you come out with a unit that doesn't make a lot of sense, move the decimal 1, 2, 3. Now you've got milliliters. Now you can measure that accurately. You can use a graduated cylinder. If you want to be really accurate, use purette, right? But this is 3 significant figures because I have 3 sig figs here and 3 sig figs here. Okay? My calculator doesn't know anything about sig figs. So make sure you understand how to write your final answer to reflect the sig figs component. Does this make sense? All right, I've got one more to try. How many grams of sodium bromide would I need to dissolve in 1.5 liters of water in order to make a 2 molar solution? I'll give you a second to jot it down and then I'll pause the video. Zoom. Now let's go over this one. Sig figs, 2 sig figs in both of those numbers, right? So my final answer needs to also have 2 sig figs. So this time the problem asks for grams. Now grams is not part of this equation at all, right? It's moles. So what I have to do is use the molarity and use the volume to get number of moles, right? So that's what my number of moles is. But the problem says, how many grams do I have to weigh out, or measure out, I should say, right? So that's why I take this number and multiply by the molar mass. Now watch this part. 308.682. A lot of students would round that to 309. But 309 is not the correct number of sig figs, is it? Right? 2 sig figs, 2 sig figs. My final answer needs 2 sig figs. So the way that you would round 308.682 to 2 sig figs would be 310 with no decimal place. Okay. Now again, I've mentioned this before. If you did everything correct, but you goofed up on that, that's the one mistake you made, is maybe you wrote 308.682, right, instead of 310. You'd lose maybe 1 point out of 5, for instance, for sig figs. If everything else was correct and I could see where this number came from, right? If you just wrote 308 and I didn't know where it came from, I couldn't give you credit. Yeah. You sure could. Yep. That'd be fun. All right, so now my great joke makes more sense now that we've talked about molarity. So you can go tell your friends this weekend when you're all hanging out. Hey, what do you call a tooth in a glass of water? A 1 molar solution, right? That's funny. This is the point where you laugh. Stick to your day job, Dr. Brooke. All right, so that's where we're going to stop for today. Stop video.